Again, welcome back. So as I told you last time, we'll see that polynomials on the real line preserve the Hausdorff dimension, and we'll generalize this a little bit, and then I'll show that this is not true for polynomials in several variables. So let me state it. So let's, for simplicity, assume that f is a polynomial. As I mentioned, if one checks the proof, one can easily see how to generalize this. And of course, I should mention that it should be non-constant, because otherwise this is not true. If we just map some set to a point, so to the constant, then of course, if this set has dimension greater than 0, the Hausdorff dimension is not preserved, because the point has dimension 0. Okay, so be a non-constant polynomial. And now the claim is that the dimension of the image is equal to the dimension of the set for a subset of the reals. Okay, so how do we prove it? Well, it might be instructive to think about it at first in monomials, or to see, well, so the basic idea is to get, so last time we had, what was it? Okay, so last time we had that if, for f continuously differentiable, this inequality. So what we want is that that we have f to be a bijection, kind of. So that's what we want, so that we get an equality here. And of course, one fact we need to get an equality is that for functions on the reals, so from the reals to the reals, the inverse of a continuously differentiable function is continuously differentiable again. So that's important. That's also a fact which is not in general true in higher dimensions. So let's see how to prove it. So let's take the zeros of the derivative of f. So we take the real roots of f prime, and now let's see what does this give us. So next we consider the intervals which we get by, let's call them I0 and I1, which is from Y1 to Y2 and so on, and then we get IM minus 1, which is just from ym minus 1 to ym, and finally IM, which is just this thing here. Okay, so what's also important to note, we left out just finitely many, or we could also say countably many. This we could also, so that's later how we can generalize it, so that these finitely many points we left out don't change the dimension of the set. Okay, so now f prime is greater or less than 0 on these intervals. So we get that on these intervals we have bijections on the image. So if we restrict f to these intervals I, then we get that this is a on these intervals, so that implies as a projection on the image, so it's just adjective. And so what does this mean? So now we use what I mentioned before. So we use this inequality here, and as it's a bijection, we get equality, as I said, because the inverse is again continuously differentiable. So we get that this dimension is equal to the dimension of f intersection I. Okay, so of this image. And now we just use countable stability, what we already saw last time. So let's see. So we get that the dimension of f is just a supremum over all these i's we had here, so from 1 to m, and then the dimension of f intersection with the intervals. And now we use the equality we have here. So that's the supremum, so this equality, sorry. And again, we use countable stability. So this is just the dimension of the union of these sets. And this is the dimension of f of f. So that's already it. So that's the proof. And now let's see, what did we actually use? Well, we used here that we have countably many intervals and on which the derivative is negative or positive. So basically all we need is that the function f is continuously differentiable. So that's one thing we need. And we need that f prime has countably many roots. And then the proof, roots of f prime. And then the proof just works exactly the same way. Well, here we had finitely many here and here, but it works just the same for countably many. So that's that. And now one more thing we can discuss. So what happens if we look at some f in a polynomial ring with more variables? So we can get a map from R to the D to R. So this gives us a map from such a map. And does this also preserve the dimension? And that's not the case. So let's see a counterexample. That's quite easy actually. So we just used a circle. So, and what do we use? So basically you can think about it in algebraic varieties. So we use this polynomial and we use f to be the circle. So that's just the set where f is 0, and this set obviously has dimension 1, or well, I shouldn't say obviously, but it's a property that basically manifolds of a property of the Hausdorff dimension, that manifolds have the dimension they should have. So real manifolds, and the circle is 1. So that's good. So this has dimension 1, and well, now it becomes easy. So the image is just the 0 point, and well, this means just that the dimension that the Hausdorff dimension of the image is also 0. Okay, so that's it for today. Yeah, I hope it was clear. If you have any questions, feel free to ask. And yeah, so I'm not sure yet if what I'll do in the next video, but well, I guess you'll see. And so thanks for watching and have a good day. Bye.